Let's finally get back to working on Tabular CFR. I want to show you an email that I got from that CUDA issue that I opened. This is a reply that I posted. I basically posted this. Thank you for the breakdown. I guess there is no need for a direct PTX backend then as expected. One thing that is weird for me is that I meant to say, right, one thing that is weird for me though is that turning the device optimizations on and off doesn't seem to affect the compilation times. So I keep them on all the time. When I'm testing things out, it would help to have a fast path. And what he's saying here is that there in fact is a fast path. It's a hidden option for now, and it only got implemented recently. Even a few videos ago, we were using CUDA 12.3, and now we were just recently upgraded to 12.6. So I'm guessing 12.5 came out like a month ago, something like that. And they're saying that this is a hidden option. It's not documented yet. So yeah, we're going to be trying this out in the future, but for now, we're just going to get back to sketching things out. I mean, I'm very happy that they're actually working on that. I mean, I don't know how much this will help, but if it speeds up things like even a few times, that would be a huge help when we were doing testing. I'm really glad that NVIDIA really cares about my experience. Yeah, it's pleasing. So let's get back to this. I want to optimize this a little for readability. We're just taking the model, applying the world ID, and this outer thing is the action ID. Oh yeah, and there is no need to use the apply pointer manually. We are doing that inside the rowgather reduce kernel. So yeah, this is going to be optimal, and I'm very pleased by this. I mean, before we start this video, let me just say a few words about what we did in the previous one. We implemented... oh, what the hell? Oh yeah, we implemented this transposing loop. Oh yeah. The reason why we are getting this error, for some reason, like, I got this message, I failed to publish the extension. And okay, if you look at the log file, it's just saying that something went wrong, please retry after some time. So we're going to have to try to publish it again. Basically, this op that we added to the language didn't work. And I just remembered right now that I think we also did, we probably did something in the change log that I didn't really note down, but I can't remember what it was. Anyway, what we have to do, let's just go into the VS Code plugin, and I'll try publishing it again. I'm just going to set the version to 9 here, and then publish the patch again. And what's the problem with this? We're never using it. Okay, that's because we commented out that line. Now let's run the PowerShell. I mean, this part did succeed yesterday, I think. So it's kind of weird that... Version 2.12.3, I mean 2.13.10 exists, but it cannot be modified. Okay, so what the hell is going on? I mean, maybe it simply didn't install Spiral. No, that isn't the case. This guy keeps getting more users. I need to get in touch. I keep saying that over and over again. I'll do it at some point. Okay. So sorry about this digression. I need to figure out why Spiral isn't showing up on the VS Code marketplace. VS Code marketplace. Spiral. And the version here is 2.13.9. Okay, you know what, forget this. Let's just try publishing it again. Like, we'll release 2.13.11 since 10 is already on the marketplace. Not bad. I'm going to pause here for a bit to... Actually, no, I won't pause here at all. Instead, we're just going to run the spiral in the extension host. Like... Let's just press Ctrl F5 here. And hopefully this time around the publishing will work. Okay, so what I wanted to talk about is that we did this loop, and this is simply like a projective loop. It goes it takes in a single dim, but it goes over all the block threads. And what it does is transposes the inputs for a given thread index inside the loop in shared memory. And please watch the previous video. I mean, it's kind of long, but if you want to know what this does, but it's basically a way of it ends up hacking the lexical scope so that all the threads get the proper data. What that means is that, for example, here we are grabbing the reward. And each thread has its own reward, but this row gather map reduce actually ends up transposing the threads. Like here we are kind of passing the thread ID, but the actual thread index would be different depending on the tensor layout. So what the row gather map reduce kernels now assure is that the correct data for the thread we actually want to be working on is being shared inside the function here. It does that by getting all the free variables from the function and then substituting them stealthily. It ends up sharing them through shared memory. And that's enough for this explanation. I'm just wondering, I wanted to add something to the changelog and I cannot remember what it is. But I guess I kind of want to... note that we released it's good. Let me pause here. I'm going to go over the commits and see whether I still have something that needs to be noted in Oh yeah. The Python main function has a device synchronization on the main stream at the end, so it catches all the trap exceptions being raised. Yeah, this is basically the only thing, the thing that I wanted to note. If you look at the how it gets compiled now, for example, pretty much anything, you'll see that we have this main, and we do a synchronization on the current stream, and this line is here so that the trap calls on the kernel aren't missed. Otherwise, it will just exit the interpreter will just exit, and the fail with calls wouldn't get noticed. That's the only thing that I forgot to note in the changelog. Oh, it's installing. Let's see. Oh, great. Okay. So now let's just commit this updated to v2 1311. We're going to close this. We're going to close this, and now we're finally going to. Oh wait, didn't I save this? Fuck. Push that thing, for fuck's sake. Okay, we're out. I'll just erase this, close this. What's going on? I want to. Yeah, I want to. I guess. What? I want to take this. Okay. So I guess I want to do this. Is that it? Oh yeah. This was it. Okay, I should have just closed the file and open it again, but never mind. Okay, finally. Sorry about the rocky start to today. Let me add this video to the timeline, and then we will start off proper. Great. Okay, so even if we tried running this, the first issue we'd have is that we cannot pass the RNG through shared memory into this kernel. Because as I was explaining, it will this kernel will get the runtime variables in a lexical scope and propagate them through shared memory to the necessary threads. And because this is a reference type, that's impossible. We just get a compilation error on the CUDA side. Oh yeah, okay. So getting the action, I do think I like this. Calculating the updates. I mean, I kind of want to go at it slowly today. As I mentioned earlier, we don't need the apply pointer because that will automatically happen inside the kernel. I'm just wondering, okay, what's going on exactly? Row gather map, reduce. We are passing in the policy current and the value, and we are doing that to the update policy. So log path probabilities, thread ID. We need the path probabilities. Okay, let me just. I'll pause for a bit here so I can reinitialize my mind. I wrote this 2 days ago, then we started working on the loop, and it kind of knocked me off course for a bit, but we can get back on it. I'm just cleaning stuff a little here. As far as I can tell, this is pretty much good. No, I want to add to the model directly. Since we're fetching this from the outside, we're going to apply the pointer here. Whoops. Sorry about that, I'm on the wrong keyboard layer. Apply PTR. This is going to add the offsets to the pointer directly, so that when it's distributed through the shared memory, it won't also have to distribute the offset in a separate variable. It's a tiny performance optimization. What it does is adds the offset to every pointer and sets the offset to 0 afterwards. Since it's a constant, it won't be transmitted to shared memory. Instead, it will just be transmitted at compile time. Honestly, this looks very nice to me now. And I've been studying this, and arguably this isn't nice. Let's apply the pointer here. Apply PTR. Simply. Okay, arguably we don't need to. Or actually, yeah, we do. One thing that we have to do is rename this because it's so confusing right now. Model policy update. Trace value update. Trace update policy. Oh, thank God. And this is going to be trace update policy. This is going to be, let's say, action ID tensor. Okay, so this is a value, and this is okay. This is a tensor. How do I deselect this one? Like, did it deselect it? I think it did. Oh, nice, it did, in fact. Okay, so I just pressed Alt and then clicked on the relevant part. So, tensor. Oh, oops, this last part I should have left out. Okay, great. So we have the trace update, trace atomic add action ID, trace update policy to the model policy update. We have to. I think we should do some. We should put some effort to separate out the trace update policy from the policy update. Oh, nice! It's showing me exactly what's going to be renamed. Trace update policy. Okay, I think this is nice. We're applying the pointer here. We're indexing trace update policy. We're passing that through as the input to the row gather void, so we don't need to apply the pointer. What about the model? Oh yeah, we are applying the pointer for that. So that's the optimization that we needed. Oh yeah, I also wanted to. We don't need this barrier city, I think, since the kernel itself, the raw gather map reduce. All the raw gather maps do have CTA barrier sync at the end, so we don't need to put them manually. Let me show it to you. No, here's the raw gather. Wait, so I guess the transposing loop is the one which has it. Just a second. Transposing loop. No, that's in core CUDA. Linear. Yeah, here it is. Barriers, CTA sync. It's right there. It's going to be a bit annoying trying to adapt this to. Try to adapt row gather. I mean, okay, row gather we don't even need to adapt for global block. I mean, for grid iteration, we just need to adapt the regular row template, not the row gather template. Okay, so this is fine. It goes down, calculates the updates, or rather, it applies the updates, the value update to the value array. Oh yeah, we need this barrier CTA sync so the results of the atomics are shown in this row map. But since this row gather already does a barrier CTA sync, we don't need that. In fact, I'm going to comment it out and row gather void above does a barrier sync. Now, I suppose we need to think about this for a bit. X policy updates. We're just passing in the model. And are we maybe getting something from the global scope? I'm not sure. Like, I mean, not from the global scope, from the lexical scope. Okay, let me pause while I think about this. Oh yeah, we're not using the wrong world ID anymore. We're because this trace update policy. Oh yeah, the trace update policy. We need to apply the pointer. We forgot about that. This is an optimization, so it only passes the pointer into through shared memory into this row gather void kernel. And the world ID. But I think that we are using the wrong world ID here. I mean, trace update policy. What about the? Here we have the action ID, so that's not the problem. This is the input and the model policy update. Oh yeah, this is what I thought was using the wrong world ID, but yeah, it's that's not the case anymore because now we have the transposing loops, and those will share the pointers. Those will share the correct pointers through shared memory. In fact, let me do it like this. I keep getting confused about what's the input for these functions, and it's easier to see if we just apply it like this. I mean, pipe it like this. Okay, let me pause here so I can think about this part more carefully. We're going to do this thinking part, and then we're going to go back to putting in print statements and printing things out. I found an error. In this model here, it should be, instead of getting from this model here, we should be getting from this X here. That was unfortunate. Yeah, I don't know why I made this mistake in so many places, but it happens. We're basically adding to the model out. Okay, let me go have a breakfast. Let's resume. I had time to have a meal and rest a little, and we'll get back into this. I think we are at the point. I fixed only, I fixed the model, and I think we are at the point where just looking at this and thinking won't give us any benefit. Instead, what we should do is go back to putting in print statements and looking at them. So for now, how about we simply try to get this to compile? That's a decent first step. And damn it, I didn't accidentally run the PowerShell. Okay, let's close all of these other useless terminals. We'll go into Spiral build file. We'll open the sidebar, go into main, and then Control F5. Okay, now let's see what's going on here. Okay, let's go to the very top. So the very top is the very first update. And the reason why it's this large is because the sampling probability is dividing the policy probabilities, and we are omitting the policy probability for our own actions. So the sampling probability ends up being a lot larger than the policy probabilities that are being taken into account. And since it is the denominator, it ends up increasing the scale of the rewards significantly. Yeah, it seems the final reward is the same thing that came in. That's good. The trace update policy are these values. Yeah, I suppose it makes sense. So what's happening is that the action that has been selected, since it's getting a negative reward, it's getting decremented by 700. And the other actions are getting incremented in equal values by 350, 99999. Let's check out the policy probabilities. Well, for this video, we're just going to take it easy. It doesn't matter too much. Well, we have the sampling policy and the policy probabilities, and this should be perfectly random. We're going to print them out. So let's just first get a sense of what is getting printed where. Here header right ln, policy current values. This is what's getting printed. Policy current and value, and this is get action. Okay, let's give it a shot. Right ln. Thread ID equals thread index. Oh wait. This is trace update policy, not sampling probes. Okay, let's try checking this out, and this should be uniform since we are initializing them from 0. There'll be a bunch of them getting printed out. Oh yeah, great. For each action being selected and for each thread. Oh yeah, okay, nice. Okay, so this is 1 action, 2 actions, 3 actions, 4 actions, 5 actions, 6 actions. So it seems we are picking 6 actions. Are we adding 6 elements to the trace? I mean, we should be. Oh yeah, we are. 1, 2, 3, 4, 5, 6. Yeah, that's definitely 6 elements. Nothing weird about this. Later we'll try out with an actual policy just to make sure that it's sampling the actions correctly. But for now, this is good for this initial step. Okay, calculate updates. That is just going to be passing the reward along. And the same probability that comes in goes out simply because the path probability. Actually, no, I didn't mean to point at this, but what I meant was to point at this. These two terms, action probability and action sampling probability, cancel out, so the same reward comes out at the end. If that wasn't the case, what would have come out at the end is either the reward being larger or smaller. Like if this sampling probability is very small, like right now it's 0. It's 1/3. But if it was something like 1/6, the reward would essentially be multiplied by 2 on every node. And it would be like 2 to the power 6, and that's 64 times minus 13, which is like 784, minus 784, something like that, probably. And or maybe something like minus 800, whatever, we can just calculate it. PowerShell, PowerShell does have a primitive calculator. Minus 13 times 2 to the power 6. And does this work? No. No. How about maybe sorry about this. Let's just write it out like 2 times 2 times 2 times 2 times 2. Yeah, minus 832. I got it wrong off the cuff. So that's basically if we held the sampling probability, it would end up increasing the reward, and if we increase the sampling probability, it would end up decreasing it, and so on. And that will be the correct behavior. So okay, the correct stuff is getting printed here. Let's print out the path probabilities. Trace up the policy. What about just the path probability? It's not here, but let's see what comes out of this. This should be like this should be multiplied by 3 on every step, I think. Yeah, the path probability is 3. Oh, it's not. It's 8. It's 9 here. What I mean to say, as you can see on the very last node, or rather, actually this is the first node. It's 3. Then it gets multiplied by 3. Then it's multiplied by 3 again. I mean, wait, it shouldn't be multiplied by 3 here. Oh yeah. It's only getting multiplied once, you know, for a different player. Like The path probability that we get here is specific to the player, so it's only getting the path probability for player 0 is only getting multiplied by 3 when we go like 2 nodes up. That's why it only goes up to 27 instead of 27 times 27. I won't bother calculating what number that is. Okay, I'll bother. 27 times 27. Yeah. If we change it to something like 1, 1, 1, you would see that we go up to that kind of update. Oh wait, and I get a sense that it's recompiling all of this, which shouldn't be the case. There is some numerical inaccuracy in path probabilities. Okay, so this push, I guess, action probability, action ID. Get action, world ID. Oh wait, I mean, this is all in the fucking CUDA kernel, I forgot. So it doesn't matter if we push the variables to runtime. No. I thought maybe that we could get it to stop recompiling on these changes if we, for example, have these variables be added at runtime only, but that's not the case. Okay, one issue that we do have is most likely that let's do some code size optimization. I'm going to show you what I mean. Okay, let's where is the get action? Here it is. And if you want to know how many times this is repeated, then just create a macro and add something like this, QEA. Then build the file, QEA. And yeah, this is getting repeated like 6 times, which isn't really the best. So instead of that, it's better to just let's do a let here. And I shouldn't have removed the QEA. Let's do a let here. Build file. And now, yeah, as you can see in the top right corner, it says 1 of 1, whereas previously it was 1 of 6. So this get action function is now only generated once, which is what we want. So, okay, calculate updates. Okay, that one might be more tricky. We can, okay, we can. Okay, the model of the trace. We're going to change some things. We're going to put the sequence. We're going to pass the sequence ID as the third argument. We're going to push it to runtime, and we're going to, yeah, we're going to put a join point here. But first, let's just confirm how many times this is getting generated. Yeah, we're going to have to fix the type errors in just a second. Right, let's actually just put something like QE, and then what will happen? Yeah, it's getting generated only once. So I guess, yeah, I guess we don't really need to factor this out. And the same would go to, and the same would go to for, the same would go for apply updates. This push function, okay, this is probably going to get generated like 6 times. Definitely. I'd be surprised if it didn't. Let me just raise the table. I did. Oh, I did put a letter statement here in this push. Maybe it would be better to instead put a let statement like let push and just leave this as it is. Okay, it's fine like this. Oh yeah, I think if I recall the previous videos, when I compiled this the first time, it was 5,800 lines of code being generated. Now it's quite smaller. Okay, that takes care of that. Trace update policy. We're going to check out the apply updates. It's just yeah, I guess that this works. Action probabilities, adjusted values. Maybe instead of calling this adjusted values, we should call these weighted values. Because we are rating them by their probability. Weighted values. Trace update value on the policy update. I guess we're going to have to okay, let's print out the action ID and the trace update value. It's actually very easy to print the stuff out now in CUDA because we've redesigned the console a couple of videos back. Actually, we aren't running into any issues with with the threads being with the threads competing for the console, like if you would use a regular printf. This is because we are using a global lock when doing the printing. Trace value update. Let's try this out. We're initializing this with cp empty. This returns an array without initializing the elements, but whenever I use this, they're always 0. So yeah, we shouldn't be assuming that they are 0, even though that's how it turns out. Oh, it's still printing out the path probabilities. This is confusing. Why is it not printing this? Console. Reward. Okay, let's build this again, then we'll run it. And maybe it's not executing this for some reason, but it definitely should be. I mean, am I not calling this? Yeah, it seems we're not calling this apply updates function. Ah, yeah, we in fact aren't. Okay, so I missed that. Okay, so what are the arguments for this? Sequence ID, model, and trace. Okay, we'll pass the sequence ID as the last argument. And I just noticed that we have this unit argument for no reason here. So it's apply updates. Okay, apply updates. And we get an error. Type case miss. Okay, online 109. Okay, so let's check it out. Type case. Where is the tensor? So is this thing here? Wait, why the hell is it like this? Wait, is this really here? Was this A and B here? Yeah, I never expected an error to show up here ever. What is the error? Like tensor body? I32, F32. Over here, it's expecting a tuple. So we're applying. So we're applying a tensor. This is happening when we apply a tensor. Where exactly? Tensor CUDA, CFR main. Tensor atomic add. Okay, I see. And this is happening in tensor atomic add, and then goes to the apply all and then apply pointer. Then it goes into apply template. Okay, have we ever actually used apply all in the past? Tensor A. I feel there's something weird here. So it's taking the tensor element. Oh yeah, so the apply all isn't correct, definitely, because the first is supposed to be getting the original dimension. Okay, that much is clear. But then the second dim returns a unit. I mean, is there any reason why this couldn't be a dim? I mean, that's what it's supposed to be. I think dim is supposed to be A star B. Even though not really. I mean, in that case, do we even need A for something? Where's the first being used? Okay, we're going to try making this change, and this could only result in type errors and nothing else. So let's try it. Can't apply a for all with a term. So this is happening in atomic add. Tensor CUDA atomic add. Okay, let's check it out. Let's check out how the atomic. Let's check out how atomic CAD is actually implemented. Atomic add for all L, array L, VL. Intrinsic atomic add. So what's the problem? However, was this tensor CUDA? Oh damn it! I hate when it. Array we cannot apply a for all with a term. So, I mean, it only has a single for all, so how could this possibly be the problem? Wait, maybe it has two for all. Maybe it has two for alls. Yeah, it has this. No, damn it. Okay, I'm just confused. No, does it like CAS also return the old value, or does it just increment? We're going to have to take a look in the CUDA manual. CUDA user, for fuck's sake. This returns an int. This returns an unsigned int. Yeah, each of them return the old value. Yeah, it seems like the atomic operations do always return the old thing. Atomic exchange. Decrement. Okay, what exactly is this one? I'm kind of confused. So it increments it only if the new one is greater than the old, something like that. Old greater or equal to the value. If that's true, then 0, otherwise old plus 1. Okay, I see. Yeah, okay, it's interesting. So we're going to have to change the signatures of these. EL. It was an honest mistake. Now, what is this thing returning? It's returning unit. Okay. Spiral build the file. What is the error now? Expected unit got F32. Iter FIRE. I mean, yeah, that intrinsic add maybe should be ignored. The result of this, I mean. What the fuck? Cannot apply a for all with a term. I mean, didn't we? Oh yeah, maybe if it's trying to apply it for ignore. We haven't opened the real core. For fuck's sake. You know. Oh, it seems like it built. Let's just take a look at this Pyro server and to make sure that it's not crashing. It isn't. I mean, when things are going well, that's when you need to be on the lookout. You cannot. You can never let your guard down in programming. You can always be ambushed by something. I guess that's kind of that does make it a bit interesting as a hobby. Okay, I forgot what this is supposed to be printing. Oh yeah, it's supposed to be printing the reward and the denominator. So it's fin reward, yeah, and it actually executes this at the very end. So this is the reward, the update for the reward, for the weighted reward, and this is the denominator. Okay, so if we divided 351 by 27, we should get 13. Yeah, it does make sense. Okay, this part is right. Okay, now what's next? Trace update, model policy update. I guess I mean we already printed out the trace update in the other kernel. The only thing that's maybe important here is that it's getting added to the right place. Let's test out that theory. We have to print out the. We're going to print out the action ID outside, along with each thread, and then we're going to print out. We're going to print it out inside. Where is this action ID is coming from? Oh, the action ID here is coming from the trace actions. And this is just the J tensor. So okay, I'm not exactly sure what I'm looking at here anymore. What do I expect to see here? I mean, this is just going to be from 0 to some number, to 0, from 0 to 3. So yeah, this is the action ID trace update policy. For that action ID, I mean, I'm not sure whether there's anything to imprint here. Yeah, every thread has the same ID. Wait, is this something that makes sense? I mean, the same thread generally has the same. I am. I'm confused. Action ID, thread ID, trace update policy. I mean, why is the action ID the same for? Oh yeah, I mean, okay, I kind of get it. Like, we have 32 threads, and they're going to iterate over this tensor locally. So yeah, okay, it makes sense that it would that the action ID would be like this. 0, 1, 2, 3, 0, 1, 2, 3. Yeah, and these are the trace update policy values. I mean, there's not much I can glean from this. Oh yeah, I guess this works now. Not much we can do here. Like, the only thing that might be suspicious is whether it's getting added to the right model policy update pointer, I mean. But because we have that transposing loop, we don't have to worry about maybe forgetting to share the correct pointer. And this was a major risk previously. Oh yeah, we're going to have to vary the rewards and make sure that a different reward is getting passed in depending on the thread. Let's go to the next thing. This is the model update. Okay, so it has been updated. Okay, how much stuff is, how large is the model? How many world IDs can there be? So it's 4096. It's this thing here. It's one shifted left by 12, and that's the same as 2 to the power of 12, which is 4096. Okay, focus me. What we are going to go to do, okay, let's print this has been updated. Since we only have like 6 old IDs, this is going to be false for most of the model. Okay, console write ln I has been updated. It's going to print out 4096 lines, and most of them will be false. I mean, all but 6 of them should be false. And I'm not going to bother looking at all of this. Instead, what we're going to do is print it out here. Now it will only print out the successful cases. And it should be those 6. Yeah. 212, 235, 212, 235, 457, 343, 790, 3447. Perfect. Okay, that makes sense. If it had been printing out some other indices, then we'd have problems. But over here, everything is fine. We're going to print out the current after the update. We're going to confirm that there are actually updates being done. Okay, this is not what I expected. What the hell? Yeah, okay, I think there's something wrong here. So let's go back to the policy update and we'll print it out. Alright, maybe I am. Yeah, I'm kind of doing something foolish, and that foolish thing is that, for example, even though this feels like we're using only a single thread here, we're actually doing 32 pushes for each of for each of these, because one thread does one push and we have 32 threads in a block, and we only have a single block right now. So what we could in fact expect to happen is that oh damn, okay, because every thread is using a different random number generator. I mean, this world ID will be updated 32 times. I mean, every world ID that's being used here will be updated 32 times. So okay, so yeah, this could happen. Like this could be 0, 0. Okay, this isn't really an error, but it kind of makes me wonder, how would I even implement all of this if I wanted to use something like only a single thread to keep track of the trace? But the rest of the thread should only be assisting the computation instead of carrying their own data. This is something that I thought about, and I came to the conclusion that it would be difficult. Okay, never mind that for now. But let's actually print out the trace updates, and I kind of want to see whether it sums up to these values, whether the atomics are working right. Let me think. Okay, where's that policy update being calculated? 4 down. There's so much stuff here. Expected value, trace policy update. Okay, so this is it. What about the world ID? Path probability, world ID, thread ID. Of course, that's not really the thread ID. I mean, is it or not? Okay, well, what are the dimensions of this? It's world ID and then the action ID. So every thread would have could potentially have different update. Alright, so every thread would have the same thing, in fact, and then what? Sequence ID, reward. The every thread could have a different action ID and the player ID. I mean, those would be the same between the threads. Okay, I'm sorry, I'm just getting my bearings again. I kind of need to keep going over and over this in my mind. So, okay, we don't need this. We need the trace update policy. World ID. Let's also put in thread ID. And this is going to be the transposed thread ID, not the actual thread ID of in the block. Okay, so the current one, so the first two are 00, 302, and the third is 312, and the fourth is 1248. So what we are looking for is the world ID 212. Oh, there are a bunch of things getting added. Okay, so this is all positive, so it's no wonder that it's great. Okay, let's take a look at the other world IDs. Okay, I think I'm going to extract this and sum it up in something like F#. F#. Okay, now let's remove all of this. Control F2, remove. And we can do a trick here, like I'm pressing Control Alt and the down arrow. Oh yeah, I should have just done it. No, not like this. Wait, did I actually accidentally ended up copying it a bunch of times? Oh, let's do it like this. Okay, and we're going to do list flatten a bunch of times, maybe. No, wait. Okay, let's bind this to a variable. Let x equals, and we see that the x is a list, and I accidentally added this here. So this is float list. We can in fact flatten it once. List concat. Let's run this in a F# interactive. Now what we're going to do is reduce all of this so we can flatten it into a single list. So okay, here's what we're going to do. We don't need to bind it to a variable. Let's leave it like this. And then we're going to do list reduce, but it's not going to be a regular reduce, but instead we're going to do a list map to, and then we are going to add the two vectors together, because we are kind of adding the list vectors together. And then let's run this. So minus 39 minus 273, 312, 1248. Okay, let's take a look at the spiral server. No, not this, but the Python debugger. $312,1,248. And the reason why these two aren't negative in the Python debugger is because we are taking a max of the actual value and 0. We are clipping the values to 0 if they are negative. Okay, so this is good. This actually does confirm that the atomic additions are working properly, otherwise it wouldn't have worked. I actually forgot about that all the threads in the block are adding the same data together. I just focus on there being the same reward, but every thread is in fact using the same world ID and pretty much the same everything. I forgot about the other parts of the data. So, okay, here's the trace update policy. Yeah, we don't need to print that out anymore. Where are we printing out the current thing? Here we are. And we are, just taking the max of the current and the update. Oh, nice. Control right element, average. Okay, this is average. I mean, we might as well. Let's print out the average. Average. We'll also print out the value. Build file. Now let's run the main. Oh, nice. After the first update, you can see that the policy average is a probability distribution. Even though this isn't good actually. Wait, why are there so many? Oh, right, because the different actions are getting selected, even though they are getting the same reward, there are multiple value updates being done, not just six of them. Right, okay. The actions are a source of randomness. The only thing that's kind of iffy to me is that this as you can see, all the values are 0 here, and that's because the last action is masked out. But this average here is in fact getting updated by something. I don't like that. Okay, so the average update is in fact wrong. The average should be 0 in the last position everywhere, much like the update. And we can probably figure out why this is happening if we think about it for a bit. So we're adding the action probability to the average. Wait, what about the current? Like, the update for the current should be 0 everywhere, I think. But wait, if I recall correctly, if you look at this, it can in fact be... Yeah, it is in fact positive in the last position everywhere. Alright, so yeah, the reason why it's positive is because we're not masking out the rewards. Like, yeah, this is something that we need to think about. So here's the expected value. It's actual probability times value. And before the first update, I mean, the actual probability should be 0 in the last element always. So this should be... Wait, shouldn't this be adjusted values or weighted values? Value. Okay, let's assume the weighted values are 0 in the last element, or at least let's assume that that's why that is what they should be, because they certainly won't be updated to be anything else. So, but the expected value will either be positive or negative. So when we take the value minus expected value, what the last element ends up being is this expected value. Okay, this is like I'm not sure what to do here. Like, do I just mask out the last element here as well? I'm considering that, but it doesn't seem like the right choice. Like, imagine the mask isn't a constant thing, but instead it varies. Like, for example, one world state might have fold be allowed, but the other world state might not, or the one world state might allow 3x spot bet, but the other won't because it's higher than maximum. So okay, this is something that I should pause on and think about. I'm simply not sure what to do here. Okay, of course, now the mask is pretty much a constant. We're just checking whether it's picking from the allowed actions. But I said a few videos back that I'm not really satisfied with converting a fold to a call if it's not allowed. Instead, in the future, we're going to bake that into the mask itself. Like, I don't want to add it to the actions. I don't want to add to the average. Let me pause here. Sorry about this. And this is something worth thinking about. I had time to think about this. And I think that it's actually another problem. That that the policy that it's never getting selected is getting updated. I mean, it's not like the value itself is getting updated. Oops. Instead, it's the current policy that's getting updated because of the because of how the because of what I just explained a while ago. So I tried simulating a bunch of cases in my mind, and maybe even though we could kind of turn off the updates for the masked out values, I don't think that that would be a good solution, because for the simple reason that even if we imagine that the policy probability for some action is 0, if we kind of imagine the enumerative CFR case where we are exploring the values that do have a policy of 0, we might get something back. And in that case, we'd still do the update, even in enumerative CFR. And that's in fact correct, because, for example, imagine that fourth action that we are not selecting is something like a fold. And that fold might have something like negative expected action. But the other actions might be... I'm not really sure how to explain this. Just a second. Okay, imagine it like this. Imagine we have an action that's masked out 999 times out of 1,000, but the other 1,000 it's not masked out, and it has some, for example, large reward. And suppose if we didn't update the policy when that action was masked out, it might end up being overshadowed by the average policy and the current policy due to their updates when it's masked out. For example, the average policy, if we masked out the updates to it, the other actions would get a lot of weight on them, and the action that's masked out would get pretty much nothing. So it would always have a low value to be selected. And the same is likely for the current policy. The current policy at any given moment in time will have a large weight on one particular action and less weight on the others. And most likely, if we don't update the masked out value, even though it can be selected, then when the actual turn comes to select it, then the current policy and the average policy won't have any weight on it. So that's why we want to do the update even if it is masked out. The most important thing is that it doesn't factor into the expected value calculation, and it doesn't. By that, what I mean is, here we are calculating the expected value, and because this action probability will be a 0 for that masked out value, it won't. If a particular action has a large reward, that won't end up affecting the expected value calculation. So I think that's really the most important thing to get right, and we do get it right, in fact, because we get the action probabilities here after we do the masking. So yeah, this is fine. It's a bit weird, but it's fine as far as I am concerned. Okay, this average threshold, I guess, is fine, since we are just decaying it after 100 updates, but this value threshold is another thing entirely, because this value threshold is based on the denominator, and that kind of depends on... Now the updates depend on how deep the nodes is in the game tree. The deeper nodes will not have much weight to them, so this might end up being actually a very low threshold. It's actually impossible to get this right. It will either be too low or too high, depending on the node in the game tree, depending on the world ID. Because the sampling probability will always be pushing up the weight of the updates. That's really a problem. I'm not really sure what to do about this. It's in fact the biggest problem with the algorithm right now. with the sampling version of the algorithm, as far as I am concerned. And I cannot think of much to do about this. I really wish. I mean, it's not possible to really offset this somehow due to the important sampling. At best, what we could do is maybe remove the value threshold entirely. Maybe set it to some high value. I don't know. Okay, so let's remove it entirely. That way we have one less hyperparameter to think about. And then we don't need this anymore. Yeah, but I do want to decay because I did get better performance when I did the decaying. I just don't know. I just don't know what to do. Like maybe do a dynamic threshold, something like that. But I mean, yeah, okay. One thing that is occurring to me right now is that maybe I should be using moving averages after all, even though that's not good either. Yeah, I don't like decaying. I don't like this. Okay, it's going to. It's. I came up with the value thresholding back when I didn't really realize we had to multiply the update by the path probability. So that's why I am getting blindsided here. But I don't think that. I don't think that using a straightforward moving average that doesn't have any exponential, I mean, that doesn't have any decay really worked that well back when I was testing things out on LIDAC back in 2021. But it's very awkward. I simply don't know what better we could do. Yeah, it's always. I mean, decaying every update. Yeah, we're going to leave out the value thresholding. It's too bad it's not like the policy update, which is kind of self-correcting. The value updates will simply have to be different. I think it would really be great if the sample probability could, for the on player, could be like 1. But in that case, we'd enter the territory of enumerative CFR. I mean, yeah, we cannot really make it one, I think. Yeah, we cannot make it one. I don't know. I guess this is one of the mysteries of Tabular CFR. In fact, because of the huge effect on the weighting that sampling distributions induce, this tabular algorithm can't really be applied to very long games, because at some point we'll simply run into numerical accuracy issues. But thankfully poker isn't a very large game. I mean, it doesn't have a lot of nested nodes. And in fact, this huge weighting increases in rewards as you go deeper into the game tree is as I explained that two or three videos ago, but it's basically why policy gradients, why this method hasn't really been adapted into the deep neural network regime. Okay, we'll leave out the value decay. And in fact, I'm going to erase that completely. I don't want this to take up mental space. Neither do I want this. Forget this. Let's get rid of this. We can get rid of this. I mean, we don't need the value. Oh. I mean, actually, we do. We do need everything. I mean, maybe we could get rid of the value from the model. I mean, are we using the value anywhere? We could make this more efficient that way, but yeah, never mind. Oh wait, I think we should be ignoring the reward here, since we commented out the console. What's this? Play unification failure. Oh, we'll just ignore here. Ignore. We'll close this. Yeah, and I do think this is good enough. I suppose what we could do is vary the reward, but I'm pretty sure that we could also vary the actions, but in that case it would be hard to actually print things out. We could what could we do? We could do multiple game steps and see what comes out of that. But I think just this basic sanity checking is good enough for me. I'm satisfied with the results so far. Okay, so what do we have to do? We have to, ignoring that, we have to make that row map global. Row map global, I mean gridwise. Make row map gridwise. And there was also another thing that I wanted to do, but it kind of vanished from my memory. Let's get rid of this. Yeah, well, what exactly do I want to do? Oh yeah, the rewards, right. Well, what do I mean by that? Well, imagine we had something like a 6-player game. In that case, it might turn out to be the case that all the players at the end of the hand might get a different reward. So in fact, rather than just having a single scalar reward, we need a static array of 6 rewards for each player. Of course, when it's a 2-man game like this, one player can only... Yeah, the rewards basically are kind of... The reward for player 1 is the opposite of the reward for player 2. So if player 1 loses, player 2 wins by that same amount. Except if you think about it, in real money poker games you have a rake, and rake is taken from the pot that is given to the winner. So player 1 loses some money and player 2 wins roughly that same amount of money, except less than that. So in order to account for the rake, we'd actually need to propagate two rewards. Okay, in that case, but yeah, we'd have two value. Right now we have two values. I mean, player 1 only needs to estimate his own reward, I think, because why would he estimated the reward of the opponents? Yeah, in fact, this is something that none of the papers really went into, but if you want to adapt the tabular algorithm for real money games, we have to think about the rake as well. Yes, we need to think about the rake. Or rather, I need to think about it. And yeah, after I think about that, multiplayer rewards, we'll make the row map gridwise, and we'll leave that as the very last thing that we need to do. For that to work, we're going to have to implement grid synchronization, and I have to think how I want to adapt the loop. And yeah, I mean, if I want to have a sequence handled with only a smaller number of threads, we have to think about how we want to handle that too. But it's very complicated, actually. I thought about it, and I could really get to a decent solution. In fact, the best solution might be to just maybe pass in fake inputs, something like that. Maybe assign world ID 0 to the threads, to some of the threads. Yeah, but that will kind of make the code a rat's nest of exceptions. It really is complicated. I mean, we have a fairly large amount of threads. When we actually do the training, 32 isn't large, but 512 is large. And I'm thinking about, what if we run it on some, complex game? We don't really want to run 512 of such games in parallel. That's what I think. Maybe we could have a large amount of ensembles, but 512 is still probably too large. How could we adapt this to a smaller number of threads? How could we... The problem isn't necessarily running this with a smaller number of threads. The problem is running this with a smaller number of threads without the rest of them just dropping off. The trouble with this is running this with a small number of threads while the rest of them are still assisting in the computation. So could we actually... Suppose we tried making this optional. Tensor set thread ID, all ID, player ID. Okay, what if the trace was optional? Here we are just thinking about the trace. Get action, calculate updates. All of this could be optional. But and then if we don't have a whole ID, how will we apply all of this? Just what will we do in the model? So yeah, the optimal solution is probably to have some kind of extraneous node and only use that as kind of the dumping ground. But the problem in that case is that there will be a lot of unnecessary computation being done. What if it never actually gets inside the kernel? Right now we are going over the entire thing. What if we just tell it to use only the first 32 threads, something like that? Yeah, why wouldn't it? We could cut off computation using that approach. We only have this like 2 times. Instead of the whole block, we could pass in a mini block in this. Yeah, it would be hard to actually allocate a union type. We could set the world ID to limit max. Yeah, we have a bunch of things that need to be doing, that need to be accounted for. Like for just normally hold them, yeah, we can get away with what we're doing right now, but in the future we might not. And so yeah, we can potentially we could leave this to we could leave this for later. I mean, we can figure out how to make the neutral element. As for the multiplayer rewards, and that's another thing that's going to really, yeah, it's going to impact the computation times. I mean, especially trying to pass in 60 rewards instead of just one. That's, I mean, we're fucking sharing those rewards through the shared memory. Maybe we'll have to start storing the reward in global memory if the thing gets big enough. Maybe, yeah, instead of passing the rewards like here, we might end up passing them as a separate argument into push. Mm. Yeah, I don't see any other choice. For rewards, we're going to have to put them in global memory, otherwise they'd be too difficult to share across all the threads. This is something that will simply have to be done. And actually, do we really need the multiplier rewards? Like in the trace element? Like, I don't think. No, maybe we do. Yeah, but it's kind of difficult. We have to find the last action for a particular player, and then assign the reward to that. Yeah, but it could work. Okay, let me pause here. I'm just maybe wasting your time thinking like this, but it really is a vital part of my process. When the task is easy, you can just steamroll through it. But when you're doing a thing like this, we're very much breaking new ground. I want to avoid having to have complex rewards at every time step. Even to, yeah, we could just put something like rewards, sequence ID, thread ID, and then the player ID. And then this would be what? Reward. Maybe that's simply necessary to set the correct expectation. And we should be propagating the rewards like that. I mean, we are propagating the low probabilities by having an array and then updating it. Maybe we need to do something similar for the rewards. Yeah, we're going to work on that next. I'm going to pause so I can finalize my thinking, and then we're going to do it. I'm thinking way too hard about this. Let's just do the rewards and move on. Like, I'm finding this part especially difficult. This part will be easy. This part is kind of easy. I'm just not sure about exactly the way I want to do it, but it's not hard. This one is a fucking nightmare. Okay, let's focus on the rewards. We have this. I press the wrong key. Shift Alt down. Rewards. And when it comes to the rewards, okay, we have the push. We have the log path probabilities. We're going to do the same thing. Rewards. Rewards. Oh yeah. This is going to be, I mean, we're going to set it off at 0. So we have the rewards. Now let's think about this. We're doing the push. And then we do calculate updates. And this reward, yeah, we're good. Instead of passing it in like this, we're going to have to set it to the rewards array. Which means we have to set it to the previous sequence index. Oh, what a pain in the ass. This is... Okay, so do you want to set it explicitly at the end, or do you want to do something else? What do we want to do here? Yeah, I mean, I wish I was just using instead of using this tensor, I'm pretty much using it for no reason. Instead of using this, I should be using something like a static array list, and that would allow me to push the stuff into it as I pleased. Tensor update. Let me finally start for the day. I've been getting up very recently. I mean, getting up very early and doing chores. I also been going to bed at 9 p.m. The games that I've been playing have gotten boring to me, and now I'm very much focused on programming. So I think we are mostly done with this. Yesterday I initiated these bullet points. I had time to think about it, and it actually isn't that difficult. And we're going to leave these 2 points for another video. I'm just going to I'm just going to illustrate how it could be done. For now, let's just take care of the rewards. So this is going to be like, for example, 13 and minus 13. We're going to pass in a list, and we're going to turn that list into a tensor. And this is going to be done in what? Oh yeah, we are going to have the reward tensor. We are going to get rid of that later. For now, let's just calculate the updates. By doing it like this, we're kind of restricting them to a subset of all possible games. You know, it might be possible that there could be some games where you have where you get rewards before the terminal episode, but we won't bother trying to capture that kind of context here. We're just going to consider the games where the rewards come at the very end. And this is going to be tensor m from list reward, and this is going to be a list reward. Oh yeah, we also have to assert that assert rewards dim equal what? It needs to be equal to size player ID. Basically, it needs to be equal to the number of players. Not bad. And there isn't really much we can do by putting in print statements in here. We're basically done with that. We've done basic sanity checking by simply taking a look at what is getting printed, and it's fine. There might still be errors, but we'll have to leave further testing in order to figure that out. After we finish this video, we're going to focus on integrating this algorithm with the games. First, we'll just get the model to run using Tabular CFR for action selection, and then we're going to do the training. And after we train only duck for the first time, we're going to compare the train policies that we get using this GPU algorithm with the one that we get from the from what we created back in 2023 in the F# series. We know that what we had in the F# series works, so we're going to compare the policies when we get to that. When we get to that point, we're going to compare the policies we get from this GPU, Tabular CFR, and the regular one. I don't trust this GPU code very much, so until we get it, until we get some confirmation that it works, and that will require doing full training, we cannot really rely on it. And I think we're pretty lucky. If we were starting out with this, it would be a lot harder to actually figure out the correctness compared to having done a lot of work on this on the CPU. I guess we'll be revisiting the F# project. And yeah, after that is done, we're going to go beyond the F# project and actually train these algorithms on no-limit call-them. I'm very much looking forward to that. Okay, so we have this tensor, and we're passing the role like this, which is, yeah, it's kind of annoying. This is the for loop. And the tensor index so we'll have to get the reward here. Inal reward equal tensor index using player ID rewards, and this is going to be, we're not going to be passing the reward like this. Okay, this is so far so good, but we have to do something with the reward that we get from this, from the kernel, from the row gather map reduce. We have to get the reduction value and set it back into the tensor. So we're going to do that. So I mean, we can just do it like this. Fun reward, and then with that reward, tensor set player ID rewards, and yeah, that's pretty much it. It's often easier to just pipe, when you have a very big function like this, it's easier to pipe its result into a lambda like this than to maybe do something like reward, and then we have to indent this. I mean, it's doable like this, but we have to add the extra indentation for this big part, and I don't like that. We don't need to ignore the reward anymore. Yeah, and this takes care of multiplier rewards. Oh yeah, we don't need this anymore. Of course, we should at least run it once to make sure that it works. Okay, just as an exercise, let me try passing an invalid number of rewards, and we'll see what happens. We should be getting an assertion at compile time. Assertion error at compile time. Rewards got to equal the number of players. Oh, not bad. Now, if we compile it like this, And yeah, we removed all the print statements, so nothing is getting printed. Yeah, it's fine. It's fine. Yeah, I very much like how this works. Yeah, this is good enough. It's good enough for this video, and I think I'm going to just segue right away into the next one. I'll add this one to the timeline, and maybe I'll set it to. Maybe I'll do the audio processing and rendering later. I mean, I already right now I cannot see it because of my head getting in the way, but it's Thursday, August 22nd, 2024, and I have a video scheduled for the next 2 weeks anyway, and I already have like 4 of them which aren't scheduled, so I'm not in a hurry to do any video editing. Oh yeah, let me just, before we end this, let me just roughly illustrate how we could adapt this to a restricted number of threads instead of the full block. Well, let's go from the top. Okay, this is test, get action, row gather reduce, and for the row gather reduce, we're going to have to basically extend the kernel so it accepts an extra parameter, which is the number of threads that are active. So we're going to be passing something like 4 here, assuming we only have like 4 active threads, and that will be it for this kernel. Now we can calculate updates. It might be a bit harder. Yeah, because we have this tensor set, so we have to do some editing. Like we're going to have to test like thread index less than 4, then what? I mean, we're going to have to do this kind of boundary testing everywhere for something like tensor set. This one is going to have to take in an extra argument. And you can see that we are doing a bunch of atomics here. This is also going to, we're also going to have to test if thread index less than the number of active threads. And over here we pass in like 4. I mean, it kind of makes it uglier, but it's not really as horrible as I thought it would be. And as for this, we're going to have to make a grid-wide kernel, which is pretty easy. We just have to go into primitives. Let's see. This is row gather. This is row. Instead of this linear loop, we're going to have to make a projective loop and blocks in grid. And this is in range M. Yeah, so it's supposed to be blocks in grid. It's not in range M, but it's in core. I mean, it's base. It's in core CUDA base, which is inlined. So yeah, this is how you turn this loop into a grid-wise loop. We just need to iterate over all the blocks in the grid, and yeah, that will take care of that. But we have to make a separate row template, which is device-wide, and I don't want to mess with that. Instead, what we want to focus on is simply integrating all of this with the game that we have. That's what I want to focus on next. I want to run actions based on the Tabular CFR algorithm, even if it's not trained. Once we cross that milestone, we'll be able to go beyond that. I will have to find a way to put this algorithm into the ML library itself. We have all the functions that we need. and they're only in the test, so yeah, we're going to have to do some refactoring in order to integrate it. But yeah, once we've integrated them into the games, this time we'll be able to actually begin work on doing counterfactual regret training for real. And we'll also be doing machine learning training using the cross-entropy method for the neural network model itself. So I do hope you look forward to that, and I'll see you in the next video.